Yeah, so today we'll be seeing about energy and social sustainability. All right, how providing energy access to communities will help in empowering them basically. So there is something called energy plus approach. So these are the contents for today. So first, as usual, we'll go through the answers from last week. Okay, and then we'll have a recap on what is sustainability, which we saw in the very first lecture, all right, 4 weeks ago. And then we have the energy system transition, what is that and what are the opportunities and challenges. Okay, then we have the United Nations Development Program. They have given guidelines for something called energy plus approach. I'll tell you what that is. Then some definitions, and then there's a case study on the Indian electricity system. So we have seen a case study on how to benchmark the urban sustainability in the first class. Now we'll be seeing about the Indian electricity system. It's almost the same procedure actually to do the sustainability assessment. Okay, and then we have the questions for this week. All right, so let's go into the answers to the questions from last week. Yeah, so first is, which of the following statements are true for a megawatt scale grid connected power plant? Okay, so what is a megawatt scale grid connected power plant? So it has solar modules. There are so many solar modules in a huge field. All right, they are all generating DC only. Okay, so there is direct current, but our systems are all alternating currents. Okay, and our transmission lines, the distribution lines, everything, they're all alternating current, right? So we need to convert that into from DC to AC, right? So we need an inverter. From inverter, it has to go to a transformer. Why do we need a transformer? This is a step up transformer, because these big power plants cannot be within the city, right, where your major load is. It will be somewhere in some remote area, some village or outskirts of some village or something like that. Okay, so the electricity needs to be transformed, and normally you do that at high voltage. This is done to reduce the the losses actually. Okay, there's something called I squared R loss that if you have studied electrical engineering, you'll know about it. I won't go into the detail. So you step up the voltage, you transmit it, and then in the city or wherever your load is, you step down the voltage again to 440 volts 3-phase. All right, and then it is distributed to the houses. So this is what happens in a megawatt scale grid connected power plant. Okay, so the right answer over here is that transformers are required to step up the power plant voltage up and down to match the transmission and distribution voltages. Okay, they do not have batteries for energy storage normally. If you want to have battery banks for megawatt scale power plants, it will take up probably even more land than the power plant itself. So it will be a huge chunk of batteries that you would require. It's not practical at all. It will cost a lot, and then yeah, it's just not practical. Okay, and also the output cannot be connected directly. Okay, so the output cannot be connected directly to the grid, because the grid is alternating current. Output of solar modules is direct current. So you need an inverter. All right. So the second question was, what is the advantage of evacuated tube collectors over flat plate collectors? Okay. The options about how much water it can handle, or what is the capacity of hot water tank, right? So you can design it as per your requirement. Okay, how much water it can handle depends on how much water you need in a day or in 1 hour or something like that. Okay, so you can design it to whatever capacity you need based on the available space in your roof. That's it. Okay, the same thing goes for the tank also. The tank, the capacity of the tank depends on how much storage you need. If you live in an area where the sun does not shine as much, okay, it's always cloudy or something, and you need like um, storage for like 3 days or something, then you can design your tank accordingly. You can design your plate or your tube collector accordingly. All right, so that depends solely on the output, to what you require. But the advantage of the evacuated tube collector is that because of the evacuation, the convection losses are lower. All right, because there is vacuum in the tube, in that tube, right? So there is no convection, that is, there is no moving fluid, so no convection losses. There are radiation losses though, but that is unavoidable. Okay. Third, which of the following statements are true? Okay, the first one was first option was solar thermal power plants use batteries to store energy. Now again, it's the same logic as the megawatt scale power plant. These solar thermal power plants are usually very big, usually of the range of megawatt, and so if you want to use a battery bank to store, you want to produce electricity and store it in a battery, then you need a huge battery bank, and that's not practical. So no, solar thermal power plants do not use batteries to store energy, but you can store energy in phase change materials, that is thermal energy storage. You can store heat, and you can use that heat during the night time to generate energy. So you can generate 24 hours a day. So that's how it works, right? Then option C was standalone solar PV systems do not require inverters. That is also not right, because standalone solar PV systems also produce DC, direct current, but you are using this to power your home, right? Or something, any appliance that requires AC, alternating current. So you need inverter for any solar application, solar PV application, unless you're running some maybe DC motor or something like that, but those are like pretty rare actually. Okay. Then the third is solar thermal power plants without thermal energy storage cannot be connected to the main grid, which is also false, because if you don't have thermal energy storage, you can still connect it to the grid, except that it won't generate after maybe 5 p.m. 5:30 p.m. whenever the sun goes down. All right, so it will be like exactly like solar PV. It will generate maybe from morning 10 o'clock to evening 5 or 6, and then it will just stop. That's it. Okay, there won't be any nighttime generation, there won't be any generation or very less generation when it is cloudy. So that's it. Okay. Number 4, what is meant by capacity utilization factor? Okay, so there are two definitions that I had told you about, right? So the capacity utilization factor is the ratio of actual energy produced to the total expected energy during the year, or you can interpolate it to a day or a week or a month also, with the assumption that it's going to follow the same curve every day or every week. Okay, that's the assumption. So so it can be it can also be expressed as the ratio of time the plant operates at full load to the total number of hours in a year. Okay, so it is either E actual, that is the energy produced, electricity produced actual, to the maximum electricity expected from that plant, the for which you have designed that plant, or you can express it as the time it operates in full load to the total annual operating hours. All right, so the correct answer is A, the ratio of annual full load operating hours to the total number of hours in a year. Number 5, is calculate the CUF, the capacity utilization factor of a solar plant of capacity 1 megawatt given its average daily electricity generation is 5 megawatt hour. So it is given that every day it's generating 5 megawatt hour. So this is for the entire year. So I can just say, okay, energy is power multiplied by time. You would have read this in school, right? Energy equals power into time. So then time equals energy by power, okay, from this one. So what is your energy? It is 5 megawatt hour. It generates 5 megawatt hour, and you have designed the installed capacity is 1 megawatt. So it operates for 5 hours in a day at full load, okay. So and total number of hours in a day is 24. So using this definition, you get 5 by 24 or 0.21 or 21%. Okay, so this is the right answer. Number 6, what is the capacity credit of a solar power plant? So what is capacity credit? It is the ratio of the minimum available power from the power plant to the installed capacity, the absolute minimum. You take the whole year, okay, that the plant is operating, and then you see what is the absolute minimum power that it is generating. So a solar plant does not generate any power during the night time, all right. So even in one day, if you see, the minimum power is 0 megawatt. So 0 divided by whatever it is, so it is 0% always, okay. The next we have identify the true statements here. So power generated from wind is directly proportional to the rotor area, which is absolutely true, okay, from this equation. Higher wind speeds will help generate more power, which is again true. It is directly proportional to the cube of the wind speed, all right. Third is the maximum fraction of kinetic energy of wind that can be extracted by wind turbines is called the Betz limit, which is again true. It is 59.3%, and this is called the Betz limit. So the answer is all of the above. All of these statements are true. And then we have the design question. How do you design a power supply system for a city if the options available are solar thermal with storage, coal, diesel, and natural gas, okay. So what you need to know or recall is that the base load needs stability, okay, and peak load requires flexibility, okay. So you need to check where your stability is and where your flexibility is. So coal based and solar thermal power plants are usually not very flexible. You cannot pump up of pump down. You cannot just take it up or down very quickly, okay. So but diesel and natural gas, they are very flexible, okay. So immediately if you have a diesel generator at your place, you will know that you can just on and off very easily, or you can just bring it to a higher level and lower level. It's pretty easy to manage that, okay. Same goes for natural gas, gas turbine power plant, okay. So solar thermal and coal are to be used to cover the base demand, and diesel and natural gas for the peak, okay. So this is the answer. Base load is coal and solar thermal, peak load is diesel and natural gas, okay. So wait one second. So do we have any doubts here, or do you need me to do some question again? Yeah, answer to some question again. I can do that. Anyone? Okay. And I'll just proceed to this week's lecture. All right, energy and sustainability. Okay. So to recap, what is sustainability? So in 1987, the United Nations Brundtland Commission defines sustainability as meeting the needs of the present without compromising the ability of future generations to meet their own needs. So, we need to consider the needs of all stakeholders. Stakeholders are anyone that are even remotely connected to any system, or a sector, or maybe a country, or even companies, right? So, and whatever decisions are taken, these stakeholders are the most affected parties. Okay, so we need to consider the needs of all stakeholders. Okay, so that includes, of course, the environment, also the terrestrial and marine ecosystems, the air, water, food, and resources required to sustain economic development into the future also. So we need to consider reducing burden on the environment, ensuring equitable development. So any development that happens, it has to reach the lowest rungs of the society. It should not be just limited to the top rungs, and only the rich people are getting richer. So that shouldn't happen. Okay, and we should do so by ensuring while ensuring that more enough resources are available for the future generations as well. We cannot just use up all of our coal or all of our petroleum resources, and 200 years down the lane our descendants won't have anything to sustain this kind of lifestyle. Okay, and to do this we need active participation from the institutions, like you have your national green tribunals, and your governments, and all these organizations, they need to participate actively in ensuring sustainable development. All right, so we'll have a look at energy system transition. Okay, so what is transition? First of all, so transition means you are changing from something that is status quo, that is something that is there today. Okay, you're changing from that to something else. Okay, that is transition. Why do you change? You change, there are many reasons for this change to occur. For instance, it could be that the resources are depleting, let's say. Okay, let's say you're using coal, but coal resources are depleting fast, so now you switch to, let's say, wood or something. Okay, in fact the opposite of this happened during the industrial revolution. Okay, people were using wood, but due to the industrial revolution there were many machines like the steam engine and everything that came, and they started using coal because of that. That is due to the transition was due to technological development. Okay, and if efficiencies are improving, or there is technological development, people will shift from one source of energy or one resource to another. Okay, and there is another reason for this transition to occur, that is recently over the last 30-40 years we have been talking about climate change. Okay, global warming. So now we are transitioning from fossil fuels to renewable energy. Okay, and we're talking about the sustainable lifestyle, right? So that is one more reason for transition. All right, so what are the opportunities and challenges for the energy system transition in India, that is? Okay, so you have the supply side and the demand side. Okay, in the supply side you have grid infrastructure. Most recently, I think about 2-3 years back, the government announced that all villages, 100% of villages are electrified. Not electrified per se, but they have the infrastructure. Okay, that the grid has reached all remote corners of our country. Okay, now it's just a question of how to expand that to individual households. That's it. Okay, so if electricity has reached your village or your town, then it's just a question of distribution of that electricity to individual homes, right? So now the challenge in the supply side is the reliable and continuous flow of electricity. So electricity has to be available, right? Someone has to generate it for it to be available. So that is a challenge. And then on the demand side, you have electricity. Of course, the connection is given, let's say to homes, but it is need based. Okay, need based means like, okay, you need lighting for, let's say, 4 hours in the evening from 6 to 10 o'clock until you go to sleep, and you use electricity only for that purpose. So you're not using it for anything else. Or it could be lifestyle. So lifestyle means when you use the electricity for mobile charging, or let's say to watch TV, or let's say for some other activity, that is some entertainment or something like that. Okay, so that is lifestyle based electricity consumption. So these two are available in many villages. Okay, the need based and lifestyle electricity consumption. Okay, so so electricity energy does not mean just electricity. It could also mean cooking, the energy required for cooking. So when we transition from wood based, the firewood for cooking, to LPG, for instance, and we had this Ujjwala program, right, from the government, where they are giving LPG cylinders to rural households. So that is part of this transition. All right. Now the challenge here is to provide electricity for social services, schools, clinics, maybe street lighting. Okay, and productive use. This is very important. What is productive use? When you are using electricity to produce something, or to manufacture something, or to create value. Okay, so like, for example, you have cottage industries and micro, small and medium enterprises, and if they use electricity in your or it could also be agriculture, right? Agriculture is also a productive use. So for pumping water for irrigation, that is also productive use. Okay, so the UNDP Energy Plus program. So what is this initiative? Okay, so initially you have connections for all. So when you have deprivation, that is if a village or if some community does not have electricity or does not have LPG cylinders at all. Okay, so these are levels of deprivation. Okay, so first what you need to do is you have to provide connections, and there are some programs for that. The government has introduced some programs for that, like Saubhagya, Ujjwala and all that. Okay, Ujjwala, like I said, is to provide LPG connections to rural households. Okay, then we have energy for all. Okay, so for basic lifestyle and social energy services, that is you have need based, like lighting and for cooking and all that, and then the lifestyle services like TV, mobile phones and all that, and social energy services for schools, hospitals and communities and all that. Then we come to the third level, which is energy plus for all. So what is energy plus? It is nothing but energy plus social empowerment. Okay, so it refers to projects, programs and interventions that promote basic social and productive uses of energy. So basic, social, of course, the community use of electricity, and productive uses of energy. Okay, so the goal of this approach is empowerment of the poor by providing access to modern energy carriers and services for livelihoods, employment, entrepreneurship, building capacity and social welfare. Okay, there are many guidelines that are given. I'm not going into that. Okay, so this is the goal of this energy plus approach. Basically, you're providing energy services, or providing energy carriers to the downtrodden or the lowest rungs of society, so that they can be empowered, they can do something with it, they can produce something, or they can get jobs. Okay, and they can create something of value for the economy itself. So how does this work? So you're providing clean and reliable energy access to schools first, So what will happen if you provide this to schools? You have improved literacy rates, right? If you provide it to hospitals, you will have lower infant and maternal mortality, better life expectancy, and easy access to quality health care. Okay, if you don't have energy access in hospitals or clinics, then it's going to be really hard. You may have to travel to the nearest town or nearest city to get quality health care, right? And yeah, you want to avoid that. Then you have the access, energy access for cooking, that is transitioning from firewood, traditional firewood, to more clean forms of cooking like LPG cylinders and so on. Okay, so this leads to reduced indoor air pollution, because when you burn firewood, it uh, it generates soot and it generates particulate matter, and there is carbon monoxide. So all of this causes pollution within the household itself. Okay, so when you use LPG, you can avoid all that, and that leads to better health of the individuals who are staying inside the house. Then if you provide energy access to agriculture, then obviously you will have more agricultural productivity, because you can use it for irrigation and fuel access for machinery, like you have tractors and all. And if you have clean fuels, like of course diesel is not clean fuel, but yeah, if you have access to fuels, then you can use this machinery, and then you can have better productivity, agricultural productivity. And then if you provide clean access energy access to industries, you have higher productivity due to better working hours. Okay, so like for example, you provide it late into the evening or something, even after sunset, then obviously they can work for more hours, or even in the early mornings and so on, right? And then of course you have the energy access to public spaces like street lighting and so on, that will lead to enhanced security and access to public infrastructure. All right, so here are some definitions. So what is meant by energy access? So energy access is the reliable and affordable access to modern energy carriers and end use services for households and communities. Okay, so the energy should be reliable. Okay, you shouldn't have, let's say, frequent power cuts or something. So, or it shouldn't you shouldn't have low voltage or frequency issues. Okay, when you're using the electricity, and it should be affordable. You should not be paying. You should not be selling your kidney to pay for electricity bills, right? So it should be affordable for people to access it. Okay, and we have, of course, energy poverty, the next one, which is the lack of access to this, to adequate, affordable, reliable, quality, safe, and environmentally sound energy services. Okay, so if you have if you don't have access to affordable energy, that is energy poverty. All right, then clean and improved cooking stoves. These are domestic or industrial stoves designed to reduce indoor air pollution and increase the efficiency of heat and combustion. Now you see these firewood stoves, they are usually open, right? So the indoor air pollution part we have covered, because they are open, and they are not very efficiently burned actually. So a lot of heat is lost to the surroundings. So to avoid that, you can use the modern cooking stoves, which increases the efficiency of heat conduction, or heat transfer to the pot or the vessel, right? Then what is an energy service company? So it is any enterprise that provides some form of access to energy and associated end use services. So it could be a renewable energy company, it could be any company that is providing, let's say, electricity access, or a company that provides LPG cylinders. Okay, so all of these companies are energy service companies. All right, then what is meant by productive use? it is the use of energy to whatever energy that they are accessing to create goods and services either directly or indirectly for the generation of income, jobs, and adding value to the economy. All right. So now we come to benchmarking Indian electricity system. So this is a case study that was conducted in 2015. Okay. So it uses the same methodology, like I said, for the sustainability assessment. Okay, I'll come to that in just a couple of minutes. Okay, so a total of 119 indicators were chosen, of which 29 were social, 46 economic indicators, 25 environmental, and 19 were institutional indicators. Okay, and we have, of course, the normalization, which, if you recall from the first lecture, I'll also talk about that in the next slide. Okay, so normalization was done by developing threshold systems, that is benchmarks for the electricity system. And they didn't stop at that. What they did is they modeled the future electricity system of India based on sustainability criteria. In 4 scenarios they considered, heroic effort, aggressive effort, least effort, and there was one more. I'll just least effort and determined effort. So based on 4 scenarios, and the future electricity system was modeled based on low carbon, renewable dominated, high reliability, least cost, and so on. These were the criteria. All right. So this is like these 4 scenarios when you don't do anything, like when the government does not do anything and lets things be as such. So that is called least effort. Then determined effort is there is some effort from the part of the government to maybe increase generation or something. Okay, and to forecast basically. So the demand for electricity will not be the same in the future as it is today. Okay, so you need to forecast and you need to plan accordingly. Okay, so so that's what this means. Determined effort. Aggressive effort is when you are aggressively involved and you do the planning and then you do the development of the electricity system. And heroic effort is something more than required. All right. So the methodology, we have already discussed this. So to measure the sustainability of the system, you need dimensions. Okay, how do you get the dimensions? So this is a hierarchical framework, right? And you have some themes that you choose, the themes to which these indicators belong. Okay, I'll cover this again in the next slide. Okay, and there are some sub themes that belong to these themes, which so these sub themes together make up these themes. All right, and then there are, of course, the composite indicators, which we have already seen in the first lecture, and then we have the individual indicators. Okay, and what are benchmarks? Benchmarks are the threshold indicator values. For each indicator you need some benchmark values. Okay, so that is required for normalization. So what is normalization? Again, it is the actual value minus the minimum threshold value that you have defined in this step, divided by maximum value minus the minimum value. Okay, so maximum and minimum values you will get from this threshold. Actual value is what you are measuring. All right, and then you have the aggregation. So once you get the normalized value, you need to aggregate to get the composite indicator value, and then the theme, sub-theme values, and then the dimension value, and finally the total sustainability score. So you can do that using either arithmetic mean, which is just the average, geometric mean is and root mean squared. These are just some methods that are used. Arithmetic mean is just the normal average. You just add it all up and divide it by the total number of indicators. All right. Yeah, so these are the themes, right? Themes and sub themes that were considered, right? So, for example, in social dimension, you have accessibility, affordability, adequacy, and productivity and acceptability. Okay, so let's take this affordability for instance. Okay, so affordability means it includes cost. Okay, if cost is huge, that means it's not affordable. Then you have the income affordability across different income groups. Okay, and then so you need to consider this availability across different groups. You cannot just say that okay, there is a rich person who can afford it, so there is a good affordability. No, you need to also consider if the poorest of the poor can afford this electricity or not. Okay, and then of course there is the availability part. The electricity should also be available. Even if you have a lot of money you are willing to spend, if there is no infrastructure availability over there at your place, then obviously you cannot access it, right? And then you have constancy of supply. These are sub themes. All right, constancy of supply, that is lower power cuts and so on. Okay, let's see in the environmental dimension, you have themes of atmosphere and environmental transition, where you have climate change, air quality, low carbon transition, and zero carbon transition. So these are so this means that when you are decarbonizing the electricity sector, but you're not exactly reaching zero carbon, right? So that is low carbon. But zero carbon is like you have reached carbon neutrality essentially. Okay, so in the base year, that is I think this is for 2013 was the base year for this study. The sustainability score was 0.377, so it is only 37.7% sustainable. And so they measured this and they've reported this. So how do we improve on this? Okay, so from 2013 what they have done is they have transitioned the electricity system to 2031. Okay, so almost 20 or 18 year gap, right? So from 2013 things need to be better in 2031. So that is what they mean by characterizing the transition. For instance, you look at the social dimension and you have this indicator, urban household electricity access in percentage. In 2013 it would have been low, but in 2031 it should be 100%. That is what we want, right? So if the urban households do not have electricity access, let's say that only 90% of them had access in 2013, we need this to be 100%. This also, rural household also, we need it to be 100%. Okay, and although like I said 100% of the villages are electrified, not the households. Okay, so we need to achieve that also. Okay, and percentage of villages electrified, this is already at 100% now. So similarly you have, let's say in the economic dimension, you have let's say share of renewable energy capacity or share of renewable generation and so on. So these are characterizing the transition itself. So from 2013 what will be the possible values of these indicators in 2031. So that's what they have measured here. All right. So so these are the values for the year 2031. So you see here the capacity utilization factor. Okay, in 2013 it was only 66%. So capacity utilization factor you've already seen. So what is the utilization in the whole year? Okay, so it's only 66%. Okay, and with these scenarios, heroic effort, aggressive effort, and aggressive effort with abundant nuclear, so they are considering nuclear power also in the scenario, okay, and in this aggressive effort with gas, that is natural gas turbine, okay, instead of nuclear, okay. And there are two other scenarios considered with solar and wind and without solar and wind. Okay, so let's look at the capacity utilization. For instance, with solar and wind, it is lower. It's only 0.63, whereas without solar and wind, it is 0.77. Do you know why that is? Because obviously, solar and wind are not going to generate all the time. So there is that intermittency here. Wind is only going to generate when there is wind available, right? And solar cannot generate at night. Okay, so because of that, this is lower, and you can see this is the same trend in all of these scenarios. Okay, and let's say average thermal efficiency of coal power plants, okay, which was 43%, or sorry, this is not in percent, this is just a normalized indicator values, so it is 0.43. okay. So in heroic effort, you want to reach up to 0.85, or more than double, almost double of this, right? Whereas in aggressive effort, you have like 0.81, and then you have similar values in the other scenarios, okay. And you look at the CO2 intensity of electricity generation, which was only 0.39 in the base year in 2013. You want to reach up to 0.66 in this scenario, okay, with solar and wind, okay. So essentially what this is saying is that under these scenarios, what will be the possible values of these normalized indicators that we can reach up to 0.66 if we go for aggressive effort with nuclear. All right, so that's what. And CO2 emissions from electricity generation per unit GDP, so you're comparing it with the economics of the country itself, which was 0.51 in 2013, and you're reaching until 0.87 over here with this. It's the same aggressive effort with abundant nuclear with compulsory solar and wind, okay. So we can reach up to 0.87. all right. So obviously when there is no compulsory solar or wind, the value is little lower, because yeah, we are talking about CO2 emissions, right? Yeah. Okay. So these are the results that they obtained for the future energy system. So as you can see, the baseline was 0.377, okay, and with gas aggressive effort with gas turbine, they reached up to 0.49, whereas aggressive effort with nuclear, wind and solar, they reached up to 0.51. So the electricity system showed an improvement of around 30% increase from the baseline, right? So from 0.377, you're increasing it to 0.51, right? And the optimum scenario is aggressive effort with nuclear, wind and solar, yeah, so that's 0.51, right? So we're at the end of this, and we'll just go into the questions shortly, but do you have anything to ask, any doubts? Was it understandable? I know it was a little dry today, because there were a lot of numbers and not much conceptual like it was in the previous lectures. So I hope everything was understandable, right? If there are no questions, I'll just proceed to the next part of today's lecture, that is the questions for this week. All right. Okay, I'll proceed. Yeah. Okay. Questions. So the three levels of energy use are, we have seen this already. I hope we were able to grasp it. So A is basic, advanced and expert. B basic, beginner, basic and social. C basic, social and productive. Or D none of the above. You want to see the question again, or do we have answers already for question number 1? And do you want to see the question? All right, wait. Okay, so the three levels of energy use. Okay, so we discussed this during that energy plus, when we discussing the energy plus initiative, right? So basic, advanced and expert, or beginner, basic and social, or basic, social and productive, or none of the above. Okay, if you want to go back to the slide, I can. All right, that's absolutely right. Do we have more answers, or do you want me to go back to that slide and explain what this is? Because we have only one answer right now, so if anyone wants me to go back to that slide, I'll do that. All right. Okay, so I'll proceed to the next question. Okay. Question 2 is, the main goal of Energy Plus program is A, to provide energy services to corporate offices, B, to produce as much energy as possible from renewables, C, to provide education and healthcare to rural communities, or D, to empower poor by providing access to modern energy services. Okay. Do we have answers, or do you want to see the question again? All right. Do we have more answers? Question again. Okay. So what is the main goal of the Energy Plus program? So your options are A, to provide energy services to corporate offices, B, to produce as much energy as possible from renewables, C, to provide education and healthcare to rural communities, or D, to empower poor by providing access to modern energy services and carriers. Of course, that's not mentioned here, but that's obvious, apparent from this. Are you sure? See, okay. See, Energy Plus is basically, what they are saying is that you have three levels of energy use, which you have seen in the previous question, right? You have basic, then you have social, and you have productive. So basic is that, and even before basic, when there are levels of deprivations, that is, you don't have anything, you don't have any electricity connection or gas connection available. The first step is to provide the connections. Okay, so you either get the electricity connection to your village or to your home, or you get the LPG connection. So that is that is the first step. Second step is you provide energy access for lifestyle energy use. That is, so then you have the basic energy use and lifestyle energy use that is coming in, and of course the social energy use. All of this is coming in the second step. Third is the Energy Plus, where you provide energy for basic, social as well as productive use. Okay, basically to empower the people to for self-employment or to be more productive, to add value to the economy. So that is Synergy Plus basically. Okay, the answer here is to empower poor by providing access to modern energy services. All right, I hope this is clear. Okay. Next is, what are the benefits of switching to modern cooking stoves from the traditional firewood stoves? Okay. A, they eliminate harmful indoor emissions and hence safeguard the health of the residents of the house. B, they have better heat transfer metrics and hence are more efficient. C, they are more convenient in terms of refueling. Or D, all of the above. So I'll read the question once again. So you're switching from traditional firewood stoves to modern cooking stoves like LPG. Okay, so what are the advantages? A is they eliminate harmful indoor emissions, and so the health of the residents are now better. B, they have better heat transfer metrics, that is because the firewood stoves are open and these are like so they have better heat transfer metrics, the modern stoves. C, they are more convenient in terms of refueling. Or D, all of the above. All right, we have more answers. Are you sure? Are you sure that it's A? A is of course correct, but have a look at the other options also. Okay, about the heat transfer and then convenience in terms of refueling. I'll just tell you, if you're using firewood stoves, where will you get your fuel from? Can you tell me that? If you're using a traditional chula or firewood stoves, okay, where are you getting your firewood from? It's not available just in a shop, right? You have to walk, or whoever is collecting the firewood, they walk to forests or wherever there are plantations, and then they collect these branches and twigs and then bring it back to their home. That's what happens, right? Whereas if you're using LPG stoves, you can just go to the agency, the gas agency, and then ask for a refill. You can give your empty cylinder, you can get the new cylinder, right, the filled cylinder. So it is very convenient in terms of refueling. Okay, it also has good heat transfer metrics because in the traditional stoves, a lot of heat is lost to the surroundings instead of just going to the pot, okay, where the cooking is taking place. And of course you have the indoor air pollution, right? So it is of course all of the above. Okay, number 4, categorize the following as per levels of energy use. So you have electricity consumption at a local clinic. B is second one is home lighting, and third is electricity consumption in a small scale factory. Okay, so you don't even have to look at the options, you can just see it right here. So first is electricity consumption at a local clinic, second is home lighting, third is electricity consumption in a small scale factory. So you have to categorize them as social, basic or productive. Okay, which one is social, which one is basic, which one is productive. Okay, so the options are given here, you can just have a look, okay, and then you can let me know. All right, So you have electricity consumption at a local clinic, home lighting, and electricity consumption in a small scale factory. Okay, these are the three. You have to categorize them as social, basic, or productive. Okay, do we have more answers? Or do you want to see the question again? Okay. Do we have any more answers? Or I'll proceed to the next question. Okay, I'll just proceed. All right. So what is the purpose of normalization of indicators? So this is something from the first lecture. All right, so you should be able to answer this. A is to ensure that the environmental dimension of the system is given more importance. B, to ensure that the system does not flout any laws of physics. C is to ensure that all dimensions of sustainability are measured equally. Or D, to standardize the indicators with different units for easy comparison and aggregation. Okay, so I'll read the question again. What is the purpose of normalization of indicators? So A is it to ensure that environmental dimension is given more importance? Or B is to ensure that the system does not flout any laws of physics? Or C, to ensure that all dimensions are equally measured? Or D is standardization, like you have two different units with different two different indicators with different units. How do you compare them? So to standardize for comparison, and then subsequently you have to aggregate them, like through arithmetic mean or geometric mean or something, because you cannot aggregate indicators which have different units, right? So what is the answer here? All right. Okay. Any more answers? Okay, I'll proceed to question 6 now. Yeah, the answer is right, to standardize the indicators, because we have to compare and aggregate them to obtain the dimension score or the sustainability score, right? So number 6 is which among the following are social indicators of the electricity system? Okay. So here are your options. A is share of coal in total electricity generation. B is transmission and distribution losses, which is also measured in percentage but is not mentioned here. C, sulfur dioxide emission per unit of electricity produced, which is measured in kilogram of sulfur dioxide per kilowatt hour. Or D is reliability of electricity supply, where you measure what is your voltage. You shouldn't have low voltages, or you shouldn't have frequency issues with your electricity. You shouldn't have frequent power cuts. Okay, so which of the following which of these are social indicators? Do you get the question? All right. So which of the following are social indicators? A is share of coal in the total electricity generation. Is that a social indicator? You need to think. B is transmission and distribution losses, which is also in percentage. C is sulfur dioxide emission per unit of electricity produced, or D, reliability of electricity supply. I'll give you an example for this reliability. Let's say you are studying for an exam, okay, and there is flickering, there is fluctuation in the voltage, okay, and it's night, so you need the light to prepare for your exam. All right, so that is something that comes under reliability. So there shouldn't be too much fluctuation of the voltage. All right. Are you sure? Okay. Share of coal. So what is? Yes, exactly. I'll tell you why. Because share of coal is something that comes under environmental dimension. It's not social. All right. It comes under environmental because the more coal you have in your electricity system, the more carbon dioxide emissions. More carbon dioxide you emit, right? So that is environmental. So D is correct. All right. The next is the lack of access to reliable energy supply is called A, productive energy service, B, energy poverty, C, social energy service, or D, energy connectivity. Okay. The question again, lack of access to reliable energy supply. So productive energy service or energy poverty or social energy service or energy connectivity. Do you have answers or do you need the question again? Seven. See, this says lack of access to reliable supply, right? So there's only one right answer here. Yes. Okay. So lack of access is energy poverty. That's it. Okay. The energy connectivity is different. When you have access to, that's exactly the opposite, right? All right. Next, which of the following are energy service companies? A is a company that builds biogas plants for rural communities. B, a company that manufactures wind turbine blades. C, an electricity distribution company. Or D, all of the above. So which of the following are energy service companies? A company that builds biogas plants, or a company that manufactures wind turbines, or an electricity distribution company, or all of these. Yes. More answers? Absolutely. All of these are energy service companies because they are into the energy service space in some way or the other. All right. Okay. So that's it for today. All right. So if you have any doubts, I can just go back to some slide or I can do the questions again. Okay. If not, I'll just stop presenting and then we can disperse for the day. All right. And I hope things were clear for today. Like if something was not clear, you can just let me know. Okay. Is there anything that you would like to discuss? Anyone? All right. Okay, so I'll just stop presenting. All right. And yeah, thank you so much for joining. And again, I'll see you next week, same time, 6 o'clock. All right. Have a great weekend. Thanks a lot. Bye.